Hey everyone, and welcome to this explainer. Have you ever looked at a drone locked perfectly in a hover and thought, how exactly is it doing that? Well, today we are going to completely demystify the invisible physics that turns stored battery energy into the raw aerodynamic thrust keeping that drone in the sky. If you want to really understand the electromechanical engineering behind three-phase brushless propulsion systems, you are absolutely in the right place.
Let's think about this seemingly impossible magic trick for a second. At first glance, a drone motor is just a stationary lump of copper wire sitting there, surrounded by some magnets. Yet when you feed it the right electrical signals, that stationary copper can somehow force a propeller to spin at breathtaking speeds. We're talking up to 50,000 revolutions per minute. And it does all of this without any physical contact pushing it around. So how in the world does that actually happen? So here's our game plan for this explainer. We're going to start with the big picture of energy flow. Then we'll dive into the history and math of magnetic fields. After that, we'll explore the physical hardware of the motor, unpack the ESC, which is basically the brain of the operation, and wrap up with some real-world reliability metrics. Let's get into it. Section 1. Energy to aerodynamic thrust. We're kicking things off with the big picture, looking at that very first crucial transformation in our electromechanical chain. You know, ditching physical brushes was literally a game changer for drone flight. In older brushed motors, you have these physical carbon brushes constantly dragging against a mechanical switch called a commutator just to reverse the electrical current. As you can imagine, all that friction means heat, wear and tear, and a whole lot of wasted battery life. Brushless DC motors completely eliminate that mechanical switching. By handing all the heavy lifting over to an external electronic controller, these frictionless motors achieve tens of thousands of hours of lifespan, not to mention an absolutely incredible power-to-weight ratio. Moving right along to Section 2, the rotating magnetic field. This is where we get into the invisible magic that makes brushless propulsion even possible. It's pretty wild to think about, but today's cutting-edge drones are actually flying on principles discovered way back in the 19th century. The journey starts around 1824 when François Arago first demonstrated rotating fields. Later on, brilliant pioneers like Bailey, Ferraris, and of course Nikola Tesla figured out how to use stationary electromagnets to create a practical rotating magnetic field. They had this massive realization that you don't actually need to physically spin a magnet to create a spinning magnetic force. Now, for the tech heads out there, this is where the math gets genuinely beautiful. Inside a drone motor, the stator has copper coils grouped into three phases, and they're physically offset by exactly 120 degrees. When you feed them balanced alternating currents, which are also perfectly offset by 120 degrees, their individual pulsating magnetic fluxes combine. When we mathematically project these three spatially displaced phases, their vector sum creates a resultant flux that rotates continuously. And the crazy part? Its magnitude is absolutely constant, sitting at exactly 1.5 times the peak flux of a single phase. But for everyone else, just imagine three people standing in a circle, taking turns pulling a heavy weight on a rope in perfect rhythm to make it spin seamlessly in the center. That constant, invisible, spinning magnetic pole is the ghost in the machine. So how does the physical hardware react to this invisible spinning force? Think of it like a dance. In older asynchronous induction motors, the rotor is induced to spin and basically chases the magnetic field, always lagging just a little bit behind. But a synchronous drone motor? Completely different beast. Its rotor is lined with permanent rare earth magnets. These magnets act like perfectly synchronized dancers, locking directly onto the rotating magnetic field of the stator. They don't chase a thing, they lock perfectly into step. This brings us to a super important concept: slip. Slip is essentially the velocity difference between that magnetic field and the physical rotor. Because our drone motor is synchronous and physically locked in, its slip is exactly 0. This is massive for drones. It means the speed of the propeller is strictly and absolutely dictated by the electronic commutation frequency. We aren't just guessing how fast the motor is spinning, we are explicitly and perfectly commanding it. All right, Section 3, brushless Outrunners explained. Now that we've got a handle on the magnetic dance, let's take a look at the physical stage where it all happens. Multi-rotors almost exclusively use a very specific design called an outrunner. In a traditional Inrunner motor, the central shaft spins inside the stator. But in an outrunner, the entire external outer shell, the bell, spins around the stationary core. By pushing the permanent magnets to the very outside edge of the motor, we maximize what's called the air gap radius. And let me tell you, this setup completely transforms the mechanical profile of the motor. Why does this matter? Well, it all comes down to leverage. Electromechanical torque scales with the square of the air gap radius. By pushing that radius as far out as physically possible in an outrunner design, we get massive rotational leverage. This exceptionally high torque density means our drone motors can spin large, high-pitch propellers directly. We can completely bypass the need for heavy, breakable mechanical gearboxes, which drastically increases both efficiency and reliability. Moving into Section 4, the brain. We're talking about the electronic speed controller, or ESC, because as we know, a dancer is nothing without a conductor.
Since we threw out those physical brushes, the ESC has to step up and manually coordinate all the currents. The ESC's microcontroller dynamically switches its array of power transistors. These are called MOSFETs, and you can kind of think of them as ultra-fast electronic traffic lights. It runs them through an exact 6-step sequence. At any given millisecond, it keeps one phase energized high, one energized low, and leaves the third one completely inactive. This super rapid trapezoidal commutation continuously drags the stator's magnetic field forward in a circle, pulling the rotor right along with it.
But wait a minute, how does the ESC actually know when to switch to the next step if there aren't any physical sensors telling it where the rotor is? That is exactly where that third inactive wire comes into play. As the permanent magnets sweep past the inactive copper coil, they induce a tiny bit of voltage called back electromotive force, or Back-EMF. By literally listening to the voltage in that inactive wire, the ESC can pinpoint the exact millisecond the voltage crosses zero. This tells the brain exactly where the physical rotor is, allowing it to perfectly time the next sequence step. It's sensorless, it's elegant, and it's incredibly smart. Quick practical takeaway for anyone building their own rigs out there. All this rapid electrical switching generates a ton of heat in the ESC's components. You really need to always maintain a 33% safety margin. If your motor draws a maximum of 30 amps under heavy load, make sure you pair it with an ESC rated for at least 40 amps. If you skip this, you risk pushing those MOSFETs into thermal runaway, which, spoiler alert, means a catastrophic failure right in the middle of your flight. And finally, Section 5, Real-World Flight Reliability and Application. Let's take all this theory, bring it out to the flight line, and see how these components actually survive and communicate out in the real world. Let's talk about how fast communication between the flight controller and the ESC has evolved. We've moved away from legacy PWM analog pulses, which were slow and added annoying latency, to ultra-fast digital protocols like D-Shot. D-Shot sends discrete digital numbers, making it super resistant to electrical noise. But it gets even better with bidirectional D-Shot. This actually allows the ESC to send live motor RPM data right back to the flight controller. The drone then uses that live data to actively filter out mechanical frame vibrations in real time. It's just a beautiful closed-loop system of perfection. What about reliability? Well, a standard brush motor might survive maybe 5,000 hours before friction literally eats it alive. But our brushless Outrunners, they will easily coast to 20,000 or even 30,000 hours of use. The only physical wear points left are the dual ball bearings. As long as you keep the dust out of those bearings and avoid cooking your stator windings by keeping continuous operation below 85% of their rated power limit, these frictionless motors are basically going to outlive the carbon fiber frame of your drone. Understanding how these metrics scale is super helpful if you're building your own drone. Notice the dramatic scaling from small to large. A tiny 2-inch micro drone needs incredibly rapid RPMs, so it requires a massive 6,000 kV rating on a low-voltage battery. But look at the heavy-duty side. An 18-inch industrial heavy lifter uses a massive stator, a high 12-cell battery voltage, and a very low, highly torquey 320 kV motor. The underlying physics remain exactly the same. It's only the mechanical leverage and the electrical limits that scale up or down. Think about what we've covered today. We have practically perfected the electromechanical chain in this explainer. From 19th century magnetic field theories to zero-slip synchronous control, sensorless ESC feedback, and near-zero latency digital protocols, we've maximized torque and basically eliminated mechanical friction. So what physics will engineers have to conquer next to push drone technology even further? Are we waiting on a breakthrough in battery chemistry or maybe the introduction of new superconducting materials? I'm going to leave you to ponder that one. Thanks so much for learning with me today.